Okay. Okay. Okay, thank you. So I'm going to talk about Pledge, which is a new mitigation mechanism that we've recently started introducing in openbsd. Okay, so first I'll just mention some stuff about openbsd in case any of you are not familiar. So we sort of started off as about 20 years ago, started off with the same sort of space as everybody else, trying to make an operating system for ourselves. And then a bunch of people thought that we'd be sort of competing against other operating systems. And we haven't really gone that way. These days, we're more sort of a research operating system, trying to develop new ideas, because many of the other operating systems out there we see are kind of locked into, they have consumers, and so they don't do change as often. So this is really what we do. We take a whole systems approach. So what that means is, if we find that a piece of the operating system is hard to secure, we'll still try to agitate in there and see if we can change something. And then if that influences us towards fixing something somewhere else, then we go and fix that. So we're always trying to find some little tweak that will change Unix in a subtle way to bring a benefit. So this is a new idea I'm going to speak about now. Another one of a series of things we've done forever. It used to be called Tame, but I renamed it because I couldn't have a conversation with anybody about tame. Because you tame something and it's been tamed, all the conjugation didn't work, so we decided to change the name into something which is a little bit better, and a little bit later you'll see why we changed the name too, because it's a little bit more clear. So, I've been involved in security for a very long time. I'll let you enjoy that for a little bit longer. That's a toy. Obviously, it's a toy. Not a toy I play with. I don't actually own it. I don't even want to touch it. That's not my hand. That was given by one of the developers to another developer. I found the first security holes in Unix in 1987. I found DNS security holes in the protocol. I found them in libc on Sonos. And then eventually I got involved, I created openbsd. And I started auditing all of the source tree in there. And it was very difficult to keep on auditing the source tree. We built quite a good team, and we keep auditing, and it just gets harder and harder. The first things are easy, and then it gets more and more difficult, and you have to think harder and harder. So eventually you realize that if you're going to have all these bugs in the system, why don't you find a way so that when a bug is hit, at least it crashes the system in a more deterministic way. So we call these things mitigations. Now, of course, that entire thing with the monkey was because that's what Loudmouth Linus called us. He went and said that we're masturbating monkeys, and simultaneously, he also was insulting all of the community around him, including all the PAX team. And he effectively has gone and created an environment where mitigations cannot be incorporated into the Linux kernel. And there's a recent article in the Washington Post that should be read by you if you're very interested in it. It was about 5 or 6 days ago. That really explains how he's actually created a culture where mitigation technologies cannot end up in mainstream Linux. And so you have Google with Android going and implementing all these things in actual product, but the mainline Linux doesn't have mitigations. I'll explain a bit more about mitigations. Mitigations are a piece that we incorporate into the operating system which will halt a program as soon as it starts misbehaving. Now, misbehaving is a strange thing to go and say. What is a misbehavior in a program? On the whole, the program's able to do just about anything, but there are certain things which it should not do. So typically we can find very narrow little things that a program is not allowed to do. An example of the first example that we really played with a lot and we introduced into the ecosystem is the stack protector. So the stack protector says that places a tiny little cookie on the stack frame. I'm certain almost all of you are familiar with this. So that overflow of that will damage that cookie on the stack. The epilogue detects it, and then the program stops. Other sorts of techniques that we've done are all very, very narrow things that a program should not do. They're intended to enforce correct behavior of a program, but we can only do it in a very small way. And it enforces these by killing the program. We have push the whole bunch of these technologies into mainstream Unix systems. So these things which are mentioned on my slide are on your phones. But how did it end up on your phones? It wasn't just that we first implemented these things. Some of these were borrowed from other operating systems, but we really pushed it into the mainstream. We integrated these into openbsd in our kernel, and then we made sure that all of the portable software that we encountered still continued running on openbsd. So hundreds of bugs in all of the portable libraries like glib and all the way up into Firefox, and everything got fixed as a result of our integration. Since those bugs got fixed on those systems, therefore the libraries were clean, and therefore it became possible for other vendors to go and adopt these technologies themselves. A strategy we take with these mitigations is they cannot be disabled, because optional security is absolutely irrelevant in this part of the ecosystem. If a technology is disableable, then it'll be disabled the first time that a user or a product manager finds that this technology is actually stopping them from shipping product. They will turn it off, and they'll never come back around to turning it back on. So optional security mechanisms are a waste of our time. We should not, I don't spend any time on anything like this. I try to make sure that all the small little things we do are completely applicable to everything in our system. And this allows ecosystem adoption in the long term. A mitigation mechanism must not have a false positive. It must grab a very nitty-gritty little detail that is illegal for a program to do. It must terminate in those conditions, and it must be It must never succeed. It must never be a case which actually occurs in a regular program. Back in the old days, people mocked it when we started introducing the stack protector, and now it's everywhere. They mocked us for this thing called WXRX, which is a policy. They went and said, oh, unlike PAX, who's got mandatory enforcement where you cannot ever allocate a page which is WXRX, which of course everybody who runs PAX has certain programs with it enabled and certain programs with it disabled. In our world, instead, we have it as a policy. We'd like to get towards where they are, but we couldn't. So currently it's a policy. But since it's a policy, we've managed to make our entire source tree follow that rule. We can't go fix Firefox yet. Actually, what's really funny is Firefox just went and added WXRX to Firefox. Of course, I don't think they did it the right way, but it's a step forward. And we'll see how that keeps on happening. So adoption of these things takes a very long time. The stack protector probably took 10 years before it showed up on phones. It requires us to be patient. Early on, a piece of software in our ports ecosystem will not be ready for these things, but in the long term, they will be. So, how does this fit into this new thing that we've done? For a long time, people have thought of mitigation methods which will allow the removal, the blocking of dangerous system calls. The typical Unix system call interface right now has about 300 system calls. They start all the way from memory allocation through to the read and write I/O calls to poll and select used for event-driven software. You end up with sysctl and I/O control, which have crazy things in them. You end up with your threading interfaces. It just goes on and on and on. And this is really, when you think about it fundamentally, this is the attack surface, because many programs don't need all these calls. But when a program is compiled, in our ecosystem, there's no way to say which program will need what thing, so we make them available for everybody. So it's not a new idea to take system calls away from programs which won't need to call them. There are some problems on the way. Libraries, which are used by programs, sometimes call these things in unexpected ways. First, let's look at what other people have done to go and deal with this problem. I don't think I need to say anything more there. I already talked about that. Right? 3 slides ago? Okay. In 2002 in openbsd, we came up with a mechanism called systrace. It was a system call interposer that could block system calls, pass them through, or even modify their results. It was a bit similar to well, it wasn't similar to anything else before, but it fit too low, at too low of a level. It really required you to be aware of what system call is that it worked at the system call level. You needed to know what the difference between open and IO control was. You needed to know all these things. And if you're a high-level programmer, you don't know what these things are. So it didn't work very well. It was also criticized because it had some time of check versus time of use issues for dealing with complicated parameterized system calls. It just wasn't very great. And it was already at that time that Niels Provos and I were arguing about the fact that wouldn't it be great if there was a way to take these system calls and group them into sort of categories. Okay, we'll get to that in a moment. So we failed to really use this thing, except for in OpenSSH on openbsd, where we use it for the sandbox for pre-authentication. And it was because we use it for the pre-authentication sandbox on openbsd that resulted in OpenSSH becoming ready for pre-authentication sandboxing, which allowed other sandboxing type models to be used on other operating systems. We first built it for ourselves and was adopted. So if you're on your Linux box today or on your FreeBSD box, you'll find various other sandboxes using their technologies fitting into this glue that we built. So one win from a piece of technology like that, a really big win, but see, this fails my test. Because it's not mandatory. We can't go and apply this principle to every single piece of software. It was too complicated. Some of you may have heard of this thing called Capsicum from FreeBSD. So it's about 5 years old. It doesn't actually block system calls. It instead goes and assigns rights to certain file descriptors, and it plays a game that some types of file descriptors could only be gotten from a daemon called Casper-D. It comes with an academic stamp of goodness from some UK academics. And there's about 12 programs that use it. So after 5 years, they succeeded at porting 12 programs to it. And all of those 12 programs show a problem, which is that intensive modifications are needed even to very simple programs. A good example to go search on the net for is go find the Capsicum version of grep and go see what they did to grep to make grep immune to bad data, to a buffer overflow in the regular expression parser. Go look at those changes and you'll give up. Because if that's what it takes to make grep do this, how are you going to apply these principles to more complicated software like a web server or a BGP daemon or an NTP server? How are you going to do that? So it fails 3 of my tests. It's not easy to use as a programmer. You cannot just go and restructure a program easily for it. It's not the applicability test that I referred to here is have they succeeded over 5 years at actually applying it to a very large body of code? And they haven't. And is the use mandatory? The use is not mandatory because of 12 programs I can't even judge whether it could be mandatory. In Linux land, a new thing is landing. Seccomp. This is basically a BPF parser run by the kernel, an extended BPF, which is Turing complete, which is going to watch your program to make sure your program doesn't do something it's not supposed to do. And my first question is, who's going to watch that BPF program to make sure that it doesn't allow something that it's not supposed to do either? And of course, we need another watcher after that. So the Seccomp program, they call it a policy, is stored somewhere else, separate from the program. So there's very easy opportunities for it to become desynchronized from a program. Especially, let's say, an upstream piece of software. Like, let's say you want to write a seccomp policy for Firefox. First of all, it sounds crazy, right? But the minute you update your Firefox, that Firefox may be calling new system calls in new ways that this program is unaware of. So now you're desynchronized. So now somebody who's an expert at writing BPF programs, or now they're writing programs to generate the BPF programs, and then they're probably going to write something on top of that. I don't see how this is going to work out in the long term. The final observation here is this BPF watcher actually doesn't know what that program is doing those system calls in that order for. So they have to come up with their own idea as to what that program is doing. And here's the problem, really. This is the simplest program that anybody ever... I didn't put Hello World on the screen because it's missing the initialization phase. But all the real programs we use in the world have these 2 pieces to them. They do an initialization, and then they have a main loop which does some sort of servicing and some sort of a task. The observation is that almost all the programs in OpenBSD do this. And of course, all programs, Firefox is an example of this as well. The initialization phase of the program ends up using a very rich set of the system calls that are provided of the 300 or so in a Unix system. But the main loop of a program tends to do almost nothing. That's an observation which we should really look at and say, there's something going on over here that hasn't been paid attention to before. So the basic idea behind pledge is this. Can we tell when a program has finished the initialization phase, where it does all those complicated calls, and entered the main loop, where it doesn't need all those system calls anymore? Is there a way for us to indicate to some sort of a watching thing that it has jumped between those two phases of the code? The crazy thing is, how about if we look at these programs and see about modifying them themselves to indicate that circumstance? So pledge is a new way of doing things. What we're going to do, our task, is to study each program, figure out what it does, figure out where the initialization phase ends and where the main loop is. We will figure out what system calls are used in the initialization phase, and we'll figure out what system calls are done in the main loop phase. And then we will ourselves, with a call we make, promise that only certain calls are needed in that main loop. So the plan, we study the source, we annotate the source code with pledge calls. The kernel is going to enforce those annotations. This is kind of crazy. Usually an annotation is just like a comment. In this case, it's going to be a comment following a fairly strict format, and then the kernel is going to follow those and say. So the annotations are promises about future behavior. I'm going to jump really right down to some nitty-gritties now. The system call we introduce takes a space-separated sequence of pledge requests. Here are a few which are currently defined. We are adding new ones as they become viable. As we discover lots of software needs certain abilities, we're doing them. The most basic one most programs do is called standard I/O. Standard I/O means the program actually needs to do malloc, obviously, because standard I/O functions tend to call malloc. So malloc is not a system call, but it has mmap behind it and munmap. It has mprotect maybe, things like that. That also means that you want to be able to read and write. So the read and write system calls are in there. And there's a couple of varieties of read and write calls. Sometimes if you're operating on a socket, you use send to or send message instead of read or write. So those are included too, with some tweaks. We have rpath, write path, cpath, and temppath. Those are ones which say that some type of open call or chmod call or anything which passes a path to the kernel is allowed to pass a path with the rpath says, I'm intending to open this path with the intent of reading from it or the intent of writing to it. Cpath is not the intent to create, but it's the intent to change the file system's path layout. That could be the addition of a file with ocreate. That could be the removal of a file. That could be a symbolic link creation. It is changing the layout of the file system by adding or removing a path component somewhere. Temppath is an annotation which is currently not enforced very strongly. Temppath says that I'm operating in /temp. I'm trying to find a way to use this annotation, place it in the source code earlier on, and later on figure out if we can build some smartness out of the fact this annotation exists, because it's a pattern which exists in code. fadder for like chmod type operations. We have separate operations for dealing with Unix and with AF Unix, that's file system sockets, or with actual internet sockets. And we have some other things like file descriptor passing ones and TTY things. And we have one called getPW, which says that this program is reasoning about looking at password entries or looking at group entries or things like that. We keep slightly extending these things. And then once in a while, over the last couple of months, we've been removing them or restructuring them. As we apply this to our entire source tree, we're learning from what the source tree tells us as to how programs use stuff. And then sometimes we're splitting this up. For example, the send and FD and receive FD file descriptor operations used to be one that was combined. And we've discovered that we have so many file descriptor passing daemons in our tree that it's very nice for us to actually reason that some of them can send and some of them can receive. So we decided to split this operation up. So I'll start with really simple examples. This is cat. So most of you can probably guess what cat does inside. You've probably read the source code before. It opens files and writes them to standard out. Pretty simple. But there could still be a bug in cat, a bug in its main loop. It's really unlikely. But if it did happen, let's be cautious. Let's follow the same policy for applying pledge as we do inside important pieces of software. Let's go crazy, and let's even do it inside cat. So cat ends up wanting to do a pledge for standard IO and a pledge for RPath, because its job is to read paths, and its job is to do standard IO operations against what it manages to open. The result of these rules are, you should look and see what is not included in that pledge statement from the previous list I kind of had. Suddenly it turns out this cannot actually write files. It cannot create files. It cannot open sockets. It cannot pass file descriptors. It cannot fork. It cannot do setuid calls, even if it's running as root. It cannot execute. In fact, when you take it down to standard IO and RPath, you realize this thing actually only has about 27 system calls it's allowed to do. Now, the rest of the program was originally written by people under the assumption it would be operating in the full POSIX environment. But an analysis of this program from down below actually makes it clear that it never uses any of those other interfaces. As programmers, we use a variety of ways to look at the code. We read it, we look at the symbol table to see what it has pulled in. And pretty soon we're able to come up with an idea as to what it actually does. I'll give another example. This is makedir. Makedir is a standard IO program. It needs to be able to create spots in the file system. That's what cpath is for. It needs to be able to read in the file system. It actually does need to do that. You have to go read the code to go see why. You'll be surprised. It needs to be able to write things in the file systems. There's a situation it needs that. And it needs fadder for the makedir -p mode, which allows you to create a file system node and actually go and set a mode on it. Once again, like cat. This program can't open sockets. It can't pass file descriptors. Can't call IO control. It can't fork. It can't exec. It can't call setuid, even if it's running as root. Very simple. And yet, as a programmer, I can go and look at this program and look at its symbol table, and I can know that this call is correct. There are some problems. There are 3 pieces of the Unix API space which will not work in this model because they use sockets underneath. They are syslog, DNS lookups, and YP, the yellow page subsystem. Ignore that if you think that's like an old school thing. We actually use it inside our libc to communicate to LDAP servers. We have a really cool thing. This will be changed later, but look at the first 2. The first one is that syslog calls occur all the way through our source tree. There are about 3,000 syslog calls in all of our utilities. So we had to come up with a way of solving this problem. Luckily, this problem was actually solved even before pledge came to the scene. In openbsd, syslog does not actually use sockets anymore. It does not open a socket and talk to the syslog daemon. It uses a native system call that we introduced called send syslog. And that is an atomic system call that does not use a file descriptor. This system call was introduced about a year ago to solve a problem. I became aware of a piece of software which, running in a main loop, something like Apache, had been attacked in such a way that the attacker was trying to figure out the stack protector cookie by repeatedly attacking the program. And each time he attacked the buffer, attacked the program, the stack protector cookie would, of course, fire. And if the stack protector cookie fires, the stack protector check function attempts to send a syslog. So your logging subsystem would eventually indicate that you have processes dying because they have buffer overflows in them. But what this attacker did is he managed to convince that program to first open up all the file descriptors. And then he managed to go and try to overflow the buffer. And the termination function for the stack protector was unable to actually go and send a log message and silently failed. Of course, since this program was a bit like Apache, it would just fork up a new process with the same cookie. And so the attacker, in theory, would eventually be able to guess a 32-bit cookie. So we introduced a no system call version of syslog to solve this problem, and it has led us directly into pledge. Pledge became possible because that was no longer a socket, and we're able to differentiate between syslog calls and programs which actually want to open an internet socket. For DNS, we've had to do something kind of similar as well. We've had to separate out the socket calls for doing DNS operations. And we do this by modifying our resolver library so it does a special type of socket call. That special system call is allowed. Other socket calls are not allowed. These are sort of cornerstones that has allowed us to differentiate between the calls, and we're going to continue this practice of going into our libc and separating things out so that they're differentiable up a little bit higher up. Something else makes pledge very easy in our tree. We have privilege dropping and privilege separation programs throughout our tree. I've had them for a long time. About 100 programs in our tree do this. So let's start with priv drop. The basic idea in a priv drop program is that it grabs its critical resource very early on. In original programs like ping and traceroute and such, as they came from in old Unix, this raw socket would be open very, very late after a whole bunch of code had run. We looked at this years and years ago, and we brought those calls up to the very top and then dropped permissions to the user actually running the program. So the result is we are already in pretty good shape from the priv drop. But since the code is this way, look what we've done. We've managed to go and put the worst case initialization at the top of the program, the initialization that needs the most privileges at the very top. And as you go down the program, you need less and less privilege. So after dropping privilege, that becomes an obvious place to go and put a pledge. And this is how our ping actually looks now. It opens the raw socket, drops the UIDs, does all the get-up parsing to figure out which way you're using it, does some socket calls to put the sockets into the right modes, and then it goes and says, hey, am I in DNS mode or not DNS mode? These are what I'm allowed to go and do. Now, the result is, once you're in the main loop of ping, it's unable to create a file in the file system. It cannot fork, it cannot exec, it can never change its UID. It's now running in a restricted version of POSIX. I think I did an analysis of this one. I think it was down to about 90 system calls that it can do out of the 300. And 90 doesn't sound that great, but some of the ones that can't run anymore are really nasty, are really heavyweight system calls. So it actually is a lot of attack surface in the kernel has disappeared. Privilege separation has also been a big thing in openbsd. We weren't the first people to do privilege separation in a piece of software. The first piece of software was postfix. Privilege separation was added so that the pre-authentication of the SSH daemon is actually spawned off and executed as a separate complete process with separate stack cookies, separate address-based randomization, whole separate policy. That thing runs completely separately and was jailed. And we used systrace actually back in those days to actually sandbox the process so it only had those specific calls that you see over there in that list. But it was about 150 lines of really nasty code dealing with this weird interface that systrace had to actually interpose and catch system calls. And there actually is a separate process which is actually doing the observance to go and see which ones are allowed and which ones are not. So it's really nice to take that complicated environment away. And now it just uses pledge standard IO. Pledge standard IO, including those system calls and one or two other, and a few more, but not really ones which introduce much risk. So in SSH, the main goal was to make sure that if the pre-auth goes and does any additional system calls, it wouldn't introduce additional risk. So it's really great. And there have been cases of people actually finding their pre-auth daemons dying. And those were actually bugs in SSHD which were then subsequently fixed. They were discovered because of the seatbelt. I'll give an example of another program that we have pledged recently. This one's important because Patch actually in the BSD ecosystem actually had 2 security holes in the last year. So these are after some refactoring of Patch to remove some really questionable code, which was exposed, 1, by the security holes, and 2, by pledge arriving at the same time. And us trying to apply pledge to the program and realizing, holy cow, this program does crazy things. We then refactored the program to not do those crazy things and do them in a much more sane way. And the result is these are the only attributes that patch actually needs. So it needs lots of file system access, but it never gets any sockets, it never forks, never execs. You can now run patch against hostile data more comfortably than you could before. Pledge actually started as a result of a rewrite of the file command, which I think is the biggest mistake program ever introduced into the BSD ecosystem. That, of course, is now turned into libmagic. And libmagic is used by a whole bunch of software which looks at hostile files on the internet and makes a decision as to whether they're hostile files, which is completely crazy. If it's a hostile file, you shouldn't have a library which will do that determination for you, but it has gone that way. So Nick went and rewrote the file command in openbsd as a privilege separated process, where the parent process opens the files and passes them to a jailed child. And the jailed child off file descriptor passings goes and actually does assessments of the files. He used systrace to do this, very much the same way that SSH used it. That was 300 lines of code. 300 lines of ugly, nasty code. And this is what it looks like now. It is 4 lines of additional code added at the top of the child process, and after the child does a little bit more work, there's another case where the child drops down. So a funny thing happens over here. What happens is a process is actually calling pledge twice. The first time it's saying, these are the I promise I will only use standard IO, get PW, receive FD, and ID from here on down. A little bit later on, it goes and says, now I need less. I promise to do even less. This is a pattern which has become very common in our tree now. We have probably 50 programs that are actually doing this levering down of abilities as they continue on down the line. So once again, no file system access, no sockets. It can't exec. The child can't do anything. All it's going to do, it's a string parsing library running inside a process. And if it goes wrong, it's just going to crash. It's going to be completely locked up by the fact it's a standard IO process which has no access to the file system. It can only deal read-only with file descriptors passed by its parent. It's totally sitting in a little jail, unable to do anything. Another program I've been very proud of working on is our NTP daemon. It has showed us how to reason about privilege-separated processes that have a lot of components in it. The NTP daemon in openbsd has been 2 processes for a while, with a ch-rooted jail which talks sockets to the outside world, a master that can set the time, and communication channels between the processes so that one process can set the time, another one can do NTP. In a newer iteration, my diagram's slightly old over here, there's another process which actually does DNS lookups in case NTP needs to do DNS lookups later on to refresh DNS lookups. That process actually is separate, has a different pledge in openbsd. And we also, of course, have this new constraint process, which is a SSL TLS lookup of the time off of some server. It doesn't go and get the time that you're going to set your machine to, but it goes and gets a time to find about a 4-second window of where the time roughly should be. That constraint is used so that the NTP UDP process can throw away messages which are definite outliers. I actually have seen openbsd people actually sending fake NTP responses to my machine, trying to drag my time off. It's really funny. It's really funny. I think it's hilarious. Anyways, I think it's a hoot. So in our new NTP, we actually have 4 separate pledges in 4 separate processes, trying to constrain so that each of them can only do very narrow things. The speaker can only open up sockets and talk to sockets on the outside. It can tell the master what it has determined the time is. The master will set the time according to that. If a DNS look has to happen, it asks the master to ask the DNS server. And the DNS server can only speak DNS to the outside world, cannot do anything else. Actually, wait, it can read the resolve.conf file. That's it. The constraint process can only gets given a socket by its master for the server it's going to go and talk to, and it's using our new libTLS, so it doesn't even need file system access to read the certificates. So it's, you know, none of these things are completely perfect, but these are steps to separate these different components of different things. Unlike, for example, the mainstream NTP daemon, that's something people should go look at. It's a complete work of art. It has like 1976 code mixed with 1980 code, generations and generations, and results in a 1 meg binary that's just supposed to deal with UDP packets. It's crazy. There's another parameter to pledge, which I haven't talked about yet. That's because it's incomplete. It's still a work in progress. The idea here is that you'll be able to provide a whitelist of subpaths that a program will be able to see. And the rest of the file system will actually disappear from the view. So it's not like a CH root. In a CH root, you end up in a completely separate subdirectory of your file system, and that becomes your new root file system. And all the rules change. In this case, with the whitelist, you'll still remain inside the root file system. But unless a particular subtree of your directory is exposed in that whitelist, you will not be able to see any of those files. So we could use the whitelist to go say that a certain program can only see /etc resolve.conf. We could say that another type of program can only go and see /user share because there's some things in there it needs. This is, we are not using this feature yet. It has been designed and it works, and we've applied it to some programs, but we're currently levering it into each of the programs to see how it is going to work and to decide if we need to change it a bit to make it more powerful. Currently, it's just a list of paths. Later on, we may want to apply different permissions to different paths. So we don't know, and so we're not finishing the work yet. We'd finish the work after we have about 100 programs converted to it. Then we'd know we're on the right track. Right now, we're not sure. Pledge is tiny. It's 1,400 lines of kernel code. Most programs which we pledge have about a 3-line diff in them to add a call to pledge and an error in case the pledge call fails. We converted 400 programs in 6 months of work. This was primarily done by myself and 4 other developers who probably all combined did about 40% of the work. So I did 60% of them myself. Xterm, for example, was pledged by 1 developer in 1 evening. That's a pretty hefty program. For somebody to reason about that program and pledge it is pretty awesome. As a result of pledging it, he also came to the conclusion that some code in Xterm should be moved around. And now he's arguing with somebody about how to move that code around. So we're going to end up with 2 improvements. One, the baseline first pledge is pretty good. But the argument is we can make it better if you move this code from here to here. That's a 2-step process. So a pretty serious programmer will actually go a bit further. They'll pledge their program and do like I just explained here in Xterm. The pledge will tell them that the program is not structured in the right way. They will try to move more initialization code up, hoist it up to the top of the program. Or in the case of a privilege separated program, they may decide that a certain component of the privilege separation is being done on the wrong side of the privilege model. And they'll move it to the other side and change the messaging between the 2 sides. This has happened in quite a few programs now. I can't even stop these people. Once they apply pledge and they know their program's not perfect, they want to go and restructure it. What's interesting though is the restructuring work stands on its own as being the right tactic. Pledge has just proven to them that their program was doing something they didn't expect. So I think this is really neat because as a result of being able to apply it to 400 programs in such a small period of time, I think we're on the way to being able to mandatorily apply this throughout our entire tree to every program. Here is the programs we've done. So I've made some of them black to highlight them. KShell has been pledged. KShell is still able to fork and execute because that's its job. It's a shell. A shell runs other programs. But KShell itself cannot open a socket because KShell doesn't need to open a socket. Its children will. When KShell forks, that forked version of K-shell still has the same rules. As soon as it execs, the new program it's running starts with its unpledged behavior. But the new program it runs is probably also on this list and pledges itself as soon as it can. Another example is gzip. If gzip itself has a bug in its decompression logic, I can now go and get .gz files from anywhere on the internet. I'd be perfectly happy to run them inside our gzip. Because our gzip now cannot open a socket, can't fork, can't exec, can't do anything. It actually is pledged with standard I/O. All it can do, once it's reading that file, is shove it out standard output, or whatever file it opened beforehand. Programs like Getty. Ping and Ping6, I mentioned them before as well. SU is pledged, but also our new doas command, which is the replacement for SU. That's a very interesting one. It actually ends up calling pledge 5 times. At the very, very top of pledge, of doas, it calls it the first time, saying that it needs about 6 or 7 abilities. Very soon after it has gone and looked at the password entries, it revokes its right to look at the password file ever again. A little bit later, it starts doing setuid calls, and after it's done those, it removes its ability. So each time it's calling further library routines that may possibly have a bug or some risk. It is removing the rights to have access to the system calls backing those. And eventually at the end, all it has is the right to exec. And then it execs, and it's done. We've also gone and done this to dig, NSLOOKUP. We've done it to the binutils linker, 2-line change. Our FTP client. So pledge is even on our install install kit. Most of the utilities on that are pledged as well. So you can go and do an install, and that FTP that's on your installer will crash if there's a bug in it speaking to some sort of a hostile download site. More utilities. Patch, like I mentioned before. SSHD for the pre-auth. We've gone and done it to tmux. Tmux actually is interesting. It has actually shown that the guts of tmux, written by Nicholas Marriott, is not perfect. So he is currently trying to refactor it to pledge it tighter. That's quite a mission. We've done it to our BGP daemon. We've done it to traceroute, TCP dump. TCP dump is a classic program that needs to be pledged. It's like the Wireshark bug of the week, right? So our TCP dump has actually been privilege separated for a very long time. It's 2 processes. One of them goes and handles the complicated things and hands it off to a chroot jailed privilege separated packet parser. Now we're actually able to take system calls away from that packet parser. Before it was jailed, but the system calls were still available. When I went through and actually added the pledge to TCP dump, I actually discovered that packet parser was still doing I/O control calls. And so I restructured it for privilege separation to redirect the final I/O control it does for statistic collection back towards its parent process. So it indicated a flaw in the design. So it's not perfect, like all of our mitigations. It's narrow. But here's the criteria I use to measure it. Is it easy to reason about this and take a piece of software that already pre-exists and modify it and start using the principles from this? Even the largest set of pledge requests you add to a program that it might possibly need is even better than actually just going and running in the full system call operational space of full POSIX. Can regular people use it? We've been getting pledge diffs from people on the internet who aren't even very serious developers. People who previously have just sent us manual page diffs are now sending us encoding diffs. Sometimes they're not right, sometimes they are right, and they're learning. They're also learning techniques for how to go and debug those programs. They're learning that they need to test every single feature that program actually has. They need to go through the manual page and test every single case that is used. So regular people can do this. It is influencing programmers to make these pieces of software better because pledge proves to them what it's doing right. It covers most cases. It's not giving anybody any false promises. Other cases of software where we have already done sandboxing or privilege separation are finding it very easy to adopt the practices. And we found about 50 bugs in pieces of software that we're doing something wrong. And as soon as we applied it, it indicated it. The way we're fitting this into openbsd is very specific to what we're doing. But I think it would be possible to actually later on re-implement this on Linux fairly easily. Of course, we have this problem that Linux finally adopts something from us, 10, 15 years down the line, because we're just a bunch of master bidding monkeys. So, pledge makes programs shinier. Okay. Thank you. Okay, are there any questions? Any questions? Nope, that's all I got. Yes? Yep. Which three? This? The plan? Or my rules? Oh, applicability. Yes. There are no watchers here. In this case, people are annotating their own program. The program does not, the watcher is directly in that program itself.
So it's more of a question of how well is your program annotated? It's always better to be.
Yeah, if you make an, yeah. So if you make the annotation for your program too strict, your program's going to crash. So you're going to have a regression. So currently what we're doing in openbsd for this release cycle is we're trying to move as quickly as possible pledging programs, and then we are going to relax so that our testers can go and find out which programs we're going to ship in a release that are broken. But a broken program is not going to end up in a privilege escalation. It's going to end up crashing, and that's going to suck. So we're hoping that we don't have too many of those cases. Yes. Yes, there was another question over there. Okay, so the question is, what about upstream packages? Will we have to maintain their pledge call, or will they maintain their pledge call? So currently, we're only doing pledge calls for our base, which has no upstream software in it. We are the upstream for everything in our base, with the exception of dig, on this list, of dig and NS lookup. Yes, 3 days ago, I could have said that we were not upstream for less, but we've decided to fork less. So this practice will continue. In our ports system, where there are upstreams, we currently have only a handful of pledge calls. We're primarily using it there for the compressors. We are terrified of those compressors, especially with compressors like XZ had 2 security vulnerabilities, like memory safety security vulnerabilities in the last year. So we'll have to see how far we can push it into that ecosystem. Now, the basic pledge call on another operating system that doesn't have pledge would be just int pledge return 0. And then this would work. So people could actually go and put an int pledge 0 into their libcs on other systems and then start using this annotation form. Now, it's unclear whether people will like the style as to how we've gone and done this. We'll have to see what happens there. It takes, like I mentioned in earlier slides, it takes a long time before people actually follow us. Yes, yes. Yeah, it's kind of a contract, yes. So the question, it's an application of contracts. Why haven't we doing this before? Why haven't we been doing this before? I have no idea. In fact, I'll be quite honest with you. I am really surprised that this has worked as well as it has. I did not expect that these particular categories, like I have here on my list, I'm really surprised that these categories actually are so applicable to most software. I'm really surprised. Like I'm shocked. And our tree is so strange. Our source tree has about 100 privileged separated pieces of software in it. So this is even more rich than most other people's source trees would actually need. Most other operating systems and even in our ports tree. For example, there are more file descriptor passing pieces of software in openbsd base than in the entire ports tree subsystem. And our ports tree subsystem has got 8,000 pieces of software in it. The first piece of software which actually did file descriptor passing in common use was SSHD. And we're using this everywhere. So a whole bunch of these features are being built in specifically because we're so used to them. And they're things that most pieces of software don't even need. So, no, I don't know how to answer your question. Why now? Why not before? I have no idea. Yeah. Okay. Thank you very much. Oh, one more? Have I got any comments from the Linux side about Pledge? There's been a few people chattering about it on and off. There was an article on lwn.net early on when it was just tame. The design has progressed quite a bit since then, and around then we were only using it at about 40 programs. Now that it's reached about 400, I haven't heard anything further, which really indicates where people's mindset is at. But I suspect there will be comments coming in the future, because I think seccomp is going to turn into a disaster for applicability. So we'll see. And I actually think seccomp will actually help them be able to do this, because they could use seccomp to catch a fictitious system call 8000, which would be pledge. They could catch it fictitiously and then create rules on top of that to change other system calls and emulate these particular behaviors for each of the system calls. So that would take quite a bit of work. It's unclear whether they'd be able to exactly match all the semantics that we have, because there's hidden semantics in here regarding what libc does. Yeah, we'll discuss this afterwards if you're still interested. Okay, yes, one. Yeah, is there hope for programs that are not in the core tree to get pledge? Well, I have a hope to add it to Firefox. A piece of this is designed for Firefox. Okay, okay, thank you. Oh. Okay, can this be done in a library for portability? No, not really. Well, like could a gigantic pledge call be in a library which goes and sets up a seccomp policy for that process? Perhaps, but I don't know how that would actually work. Because the seccomp interface is one of the first things you'd want to take away from a program on the first pledge call. So the delevering it's going to be a problem for them. So yeah, I'd have to talk to someone who's a seccomp expert to see if I can help them with that. Yeah, because I'm willing to change the semantics over here to make it easier for other systems to adopt it. This is still early. We can still move this API slightly off towards the side to make it easier for somebody else. So, but in 2 to 3 years, this will be harder for us to go and do. Okay. Thank you very much. We'll take this offline.